Good morning, good afternoon, and good evening. I'm Xiaokui. Welcome to the Kestrel hunting session at Black Hat 2022. In this session, we will get a sense of systematic and reusable hunting with Kestrel. We will also learn how to use OpenC2 and Kestrel together to apply pre-programmed hunt books on different data sources to hunt automatically. Kestrel is a cyber threat hunting language. The language lifts the business logic of a hunt up from your data sources, your EDR systems, your log stores, and your SIEM systems. Kestrel empowers you to reuse, to compose, to share your hunts, and not repeat yourself. To start, let's search Kestrel in your favorite search engine. And then go to the main Kestrel repo. Open Cybersecurity Alliance Kestrel. The repo contains all links to start. Installation how-to, language tutorial, Kestrel blogs, past talks, and links to the Kestrel Huntbook and Analytics repo. Now, let's launch your own Black Hat demo from here, and feel free to start us. The link will bring us to a binder sandbox, ready to compose and execute hunts. And this hunting lab we prepared for the Black Hat Arsenal actually belong to a purple team event, while the red team used Caldera to conduct a cross-host attack campaign. We monitored the entire network of hosts and released data for the blue team event we are going to do today. There are 4 tasks we are going to touch today. First, we will search for TTPs from simple to complex, from specific to generic. We will get a sense of knowledge abstraction and revisit automatic hunting with generic TTPs in the last task. Second, we will discover different parts of the attack on one host. Then follow the data flow associated with the lateral movement to discover the entire attack campaign across hosts. Third, we will upgrade our hunts with analytics. The white box or black box detection logic one can invoke in a Kestrel hunt flow to gain information besides querying a data source. Lastly, we will walk through an example, given some points to investigate, how to use an OpenC2 command to instantiate and execute a Kestrel hunt flow, then harvest results for further response actions. Okay, let's start. So the first part, we will start search for some TTPs. And there are 3 hosts we are going to touch: 2 Windows box and a Linux box. And we know there is a email client, WinMail, running on the first Windows box, and there is a vulnerable Node.js process on the Linux box. We know that the red team is using Caldera to do their activities, and there are pre-programmed techniques. For example, 1057 in the procedures like discovery that is usually called by Caldera agents. So the first simple task, if we can match anything on the Windows box, one of the Windows box, that there is a PowerShell executed by a Caldera agent, maybe, which contains some command line, like a fingerprints in the command line that we see here as a PowerShell script. That will be interesting. So very simple first task, that we get back a PowerShell on the first machine. We should be able to see the same thing if we match it for the second machine. probably with different PID. Exactly the same thing, because this is the typical Caldera technique for 1057. We can do similar things for identify local user or antivirus program, which is very straightforward, and we can match all the processes of such processes on the first machine or second machine. That's very easy. Can we do a little bit more abstraction so that can we match a group of techniques that are related or similar to each other? For example, in lateral movement, usually the attacker may get a way to move from one machine to another, and he will use the same way access to first deliver a payload to the target, second launch a payload on the target. So in this example, Caldera uses Windows remote management through a PowerShell script. That if we can match a PowerShell script with this kind of a shared components between the two, we should be able to match two techniques together in one match. So that return will be processes that conduct both 1570 and 1021. Let's see. We display the return with command line, and this one is the 1570, and this one, the starting of a process, is 1021. Okay, that's easy. So we believe that this is simple for technique matching. When we go to more generic TTPs, we believe every TTP can be described as a graph pattern. That it can invoke more than one entity, one process, one file, more than one network traffic, and there are some relations you can describe between them. If we try to match a graph pattern, we should be able to match entire TTP. And we can be more generic. Here is the same pattern we try to match, that a process has a parent process that is not the binary of the process, which can be exploited. That a web service is exploited, forking a node that is not the worker process. It can also be a phishing email, that the email client is trying to get something not typical email client activities as a spawn process. As a result of the match, you can see that we matched it both on Windows and Linux for phishing email activities and exploit, as a Splunk is an exploited process from Node.js. Okay, now let's go to the second task, entire attack campaign discovery. So we get a threat hypothesis from the threat intel team that the attack starts from a phishing and it has a lateral movement to a Windows machine. We need to discover which machine it moves to and whether it successfully moved to that. We also need to discover whether it also tried to move to a Linux server, which server it is, and whether it succeeds and what activities it did on the Linux server. Lastly, we need to discover what is the C2 IP address. Okay. So we will start from the phishing TTP that we talk about in the first hunt here. That after we matched anything spawned from Winmail that is not Winmail, we see two things. This may be common for opening a web page, but this is absolutely not common. This could be a very malicious thing as an attachment opened, a CMD. And let's just get the CMD part of the entire thing, so that the phishing candidate variable is a Kestrel variable that contains two different processes with two PIDs, right? And we can further filter that for only one PID from these four PIDs. Kestrel is an entity-based cyber reasoning paradigm, so that use processes, files, users, email address, network traffic and things as entities to reason about a campaign. Threat hunters do not touch raw records directly, and Kestrel will extract all the entities and lift them from the records and build the relations so that threat hunters can think the campaign from the entity perspective easily. That means we need a very, very powerful capability, relation resolution. We need to move from entity to its neighbors, to its connected entity. We already know there is a command that executed by windmill. What's the result? What's the impact of it? Can we find its child process? So we can find the child process created by the command, which is a PowerShell. Okay, it's not the end. And let's do that same thing. Let's find the child process of the PowerShell, which is Splunk. Okay, this is something more interesting. It looks like a Cadera agent. Let's further drill down to find out all the child processes of Splunk. Wow, this time we get many malicious activities the attacker did, including the lateral movement processes we see previously from here, right? As well as something like this one. Looks like a sophisticated malicious payload to exploit something. We will further drill down. So now we already investigate the first machine. And let's follow the network flow from one of the lateral movement process to check what is the target of the lateral movement and whether it succeeds. And the first one we want to check is this one. We just filter the Splunk activity processes down to one process, and then list all the narrow traffic from the process. Now we can see that what is the destination that the attacker is going to lateral move to. Luckily, we have monitored the machine and we can query that machine as well. We can query the second machine and then to find the same narrow traffic, but from the perspective of the second machine. You see they are almost the same, but this is data from the first machine and this is data from the second machine. From this narrow traffic, we can further find what is the process creating the traffic on the second machine. On the first machine, it's PID 7028. On the second machine, it's PID 4. Unfortunately, this is a system, very system process, as Sysmon does not monitor the activity of it. We lost the clue. However, it's okay because we know that from command line, the attacker should be able to try to launch a Splunk on the target when he later move to, and we can see if he succeeds or not. We can check Splunk processes and all its child processes as its activities, and we can find the Splunk process running there and all its child processes to get all the activities of the attacker did. That's good. So next, there's another lateral movement we will try to track, which could be exploited to a Linux box. Let's get the second lateral movement part, 7880, which is here. We will do the same thing. That's list narrow traffic from this process, which goes to the Linux box that we know. And then we will find the narrow traffic, same narrow traffic on the Linux box using the reference to the previous Kestrel variable, the same source port, which will identify the narrow traffic from the Linux box perspective. The IP address is a little bit different because there is a container running there, but we can find the process on the Linux box, which is a Node.js application. From there, if we do further drill down to find its child process and its grandchild process, we will further to find what the attacker is doing. So the child process of the exploited Node.js process is Splunk, which is the Cadera agent. And the grandchild process are all the activities that the attacker did on the Linux box. You can see a lot of things like a beaconing activities at the end, so that if we get all network traffic from the grandchild processes, maybe there are some other network traffic to other places, but if we get all of them, we will be able to see the potential C2 hosts as one of them. At a larger chance, I think it will be this one, because this command line indicates this is more like a C2 server. Now we have done the data retrieval part. We need some analytics to help us confirm the beaconing activity on these hosts and other more complex analytics besides data retrieval. Okay, now it's time for the third handbook, apply analytics. So we have done a lot of data retrieval. However, hunting is not only about data retrieval. We need to apply very complex logic, or even detection logic not written by us in black box, to do some more complex reasoning. We also need to visualize data to help us digest what is happening. We also need to include threat intelligence and different type of information, such as domain name, geolocation, IP address, to help us reason about the campaign. So in Kestrel, one can apply any external logic not written in Kestrel, like written in Python, written in Perl, written in C, in Java, as a single hunt step. We call it an analytics hunt step. So example here is after one finds the Splunk D process and lists all the network traffic from Splunk D on Linux, we will see all the destinations. We can simply use an analytic called domain enrichment that's in the Kestrel Analytics repo, open sourced, belong to one of the analytics here, to use whoislookup to do the whoislookup live and enrich all the destination IP addresses with the domain name. So before the enrichment, before the analytics, we print out all the attributes here of the traffic variable. And after the enrichment, we printed again the attributes of the traffic variable. We see something new. Those are the two new attributes generated by the analytics. So that now, besides the IP address, we can also print out the domain name and organization. Similarly, we can apply analytics to generate visualizations. So this one, also open sourced, will find the geolocations of IP addresses and then ping them on a map. Not only doing enrichment and visualization, analytics can be used to apply external logic, detection logic. So if we get network traffic from the Splunk D processes and some suspicious network traffic that we suspect those could be C2 connections, we can apply analytics to reason about whether this is a beaconing behavior, given all the timestamps we have here, or we can simply use a visualization to plot all the network traffic to think about the seasonality and the trend of it, whether this is more like a beaconing behavior. Analytics is just a one hunt step. It's not the end hunt step, the last hunt step. One can do pattern matching, one can do relation resolution after analytics is done. So analytics just to give you extra information or extra decision or vision when you are thinking about what you already gain from the Kestrel variables. So you can do it filtering things after the analytics. So we have talked about the Python analytics interface for Kestrel, and we also have Docker interface that allow you to run anything, even proprietary binaries that you don't have access to, the access to the source code. That's fine. And we are planning for analytics running in the cloud and analytics using existing knowledge from other repos as well. Now we finished the 3 handbooks. Next, Ian will take us to OpenC2 to instantiate and execute Kestrel hunt flows automatically.
As you've just seen, thread hunters can now work in a familiar Jupyter Notebook environment for all their thread hunting needs. They can search their data for TTPs, run analytics, and visualize the results. And since they're using Kestrel, they're happy thread hunters because they can do this across all their different data sources, regardless of the query interfaces that are native. But what if you want to automate your thread hunting? For example, schedule thread hunts to run automatically, respond to new threat intelligence, or investigate an alert that just popped up in your SIN. Using the new Kestrel OpenC2 actuator, you can do just that. OpenC2 is a vendor-agnostic command and control specification from the Oasis group. In OpenC2, a producer will issue commands, in our case, a request to perform a hunt, and a consumer will execute these commands and return any results. In our implementation, we use HTTP and JSON serialization for command and responses. Let's take a look. Now for this part of the demo, we'll be using the Calling Kestrel via OpenC2 notebook. Now at the top of the notebook is a brief description of OpenC2 if you're not familiar. Now there are 2 important things to mention. The first is that any command in OpenC2, it contains an action on a target. An action is what we want it to do. In this case, the main action that our Kestrel actuator supports is investigate, which allows us to return more information about a target or to run a hunt book on that target. The second thing to note is that OpenC2 is a producer-consumer model. Now, we need to run a consumer to automatically catch and execute any of the commands that we might send to it. We've run this binder environment to automatically run the consumer, but in case you didn't run it that way and you need to do it manually, you can invoke it using the Python consumer.py command. Once it's running, let's get started. First thing we'll do is import a couple libraries that we need and specify where our OpenC2 consumer is. In this case, it's running on localhost with the port 5000. Next, we'll add a couple of helper functions and define our first command. Now, the query command for an actuator will return everything that it supports. All the different actions that it runs on and any additional information, which we'll see in just a second. Next, we have a simple function which allows us to actually send the command to the consumer and process the results we get back. Since we're just using HTTP for our transport, we're using the Python request command to send some JSON commands to the OpenC2 consumer and getting the results back. So let's run that. And now we can send our first command, the query command, to our OpenC2 consumer. Now what we can see here is that our actuator supports the investigate command and has a couple of options that are specific to it. And we know these because they're prefixed with Kestrel. And what we see here are a list of any of the hunt books that we can run, such as an anomaly hunt book or an exploit hunt book, and any return variables that they have. For example, the exploits returns an exploits variable in that hunt book, and then any variables that the hunt book needs to take in order for it to execute. In this case, the source in which the hunt will run on and the process name. This is the one input this hunt book needs. Now, if the source is not passed in, the consumer can be set up and configured with various default values. So let's see what a first hunt might look like. So we have the exploits hunt book, which, as we previously saw, takes just the process name. And we want to run this in the default default data source. Now what we're going to do is we're going to pass in the process node. Now the exploit hunt book is set up to find any process that spawns another process that is not itself. So a process node spawning a process that is not node. And so when we run this, you'll see it'll quickly return the results, which we can put into a pandas data frame for some nice, easy visualization. To show you how we can reuse that same hunt book, we get the same exploits hunt book. In this case, we're going to send it a different data source. In this case, it's a Windows data source, and we're going to send it a different process name, this windmill. And again, when we run it, we see that now it contains any of the Windows data. So we've now seen how to use OpenC2 and the consumability and composability of the hunt books to run across different data sources. And in case you're wondering, you can see that yes, the name of the process and the parent are different, and this is as a part of the results that were returned. If we don't want to write our OpenC2 commands manually, we can use the Oasis OpenC2 Python package to help us do that. So let's import it and run a couple of hunt books using commands that we've actually composed using this package. So the first thing we're going to do is we're actually going to specify which hunt book we want to run. This is the check C2. This is checking for command and control traffic. And we're going to query the profile for that hunt book to get any information about it. In this case, we know it has two return variables, the traffic that it potentially saw and the processes connected to that traffic. And it takes two different inputs, the source that we're going to run against and an IP address. So what we can do now is we can create our OpenC2 command. Well, we'll pass in an IP address that maybe we got from a threat intelligence source. And we'll note that this is an investigate action. We're running on that target, and we've automatically passed in the return values and the hunt book that we want to run. If we want to see what that command looks like, we can serialize it and see that it's the familiar JSON format that we saw before. And we can now send this new command to the server and get the results back. And because it returned two different results, one is the processes that had the network traffic that was associated with that IP address that we passed in. And the second is any of the traffic that we saw. So what we've seen here is how we can leverage OpenC2 to automatically run and parameterize our hunt books across all of your different data sources.
Thank you for watching. Now it's your turn to play the blue team in the sandbox. To learn more, to find us on Slack, to contribute, to share your hunting story, or to talk to other hunters, just visit the Kestrel land repo for all the links. Happy hunting, everyone!